Okay, so he is there since 2003. He did his PhD from Applied Science Mathematics Department under the supervision of Professor GIAN in fixed point theory and applications. Okay, and then on his name, total 250 research articles. You can understand, 250 research articles in the referred journals, and he guided 16 PhD students, and he has delivered his talk in many parts of the country and abroad, many countries. Okay, and his research in quantum mechanics, cosmology, non-linear dynamics, and functional analysis. Okay, so on my invitation, he is an Indian expert. Okay, because you know very well that for the GIAN program, only one foreign expert can be provided, and the remaining Indian experts that we have to arrange. And as I said, we have the lot of different process for this. So, as an Indian expert, he is one of the experts here to deliver a talk on fixed point theory. So, I think yesterday itself I told you that he will talk on fixed point theorems on fuzzy metric spaces. Okay, so you have very good idea of the fuzzy sets and fuzzy logic as our MSc students, his final year students, they have an optional paper. It is like a compulsory paper. You can assume that they are learning this fuzzy sets and fuzzy logic almost for 2 semester course. So they have the good idea, as well as the other students also, they have a good idea about the binary operations, binary relations, etc. So may I invite Professor B.S.Choudhoury to deliver his talk, please.
Good morning, everybody. So I see in front of me research scholars, faculties, and students. So may I know how many of you are students? May you raise your hands? Only students, please. And all of you, I presume, are postgraduate students, in a good number present here. And it's a privilege for me that I have been told that you are having in 2 semesters 2 courses in fuzzy logic and rather in fuzzy mathematics. So I am privileged that, as you know, I think the abstract has been distributed amongst you. I am going to speak on some aspects of fuzzy fixed point theory. So it will be convenient for me that for the students I can give you some exposure on that. Essentially, I will dwell on our experiences in dealing in the research area of fuzzy fixed point theory and related things. I think if you follow me with proper attention, then the things will also be intelligible to you, the postgraduate students. I will try to be expository in what I will say. As you had been, I was informed and came to know Professor Dorel Miet has given you a good exposure of what is a fuzzy metric space. And I should repeat that Professor Biramani from IIT Chennai has done a great job in introducing the idea of a fuzzy metric space. You see that fuzzy is a very flexible concept. And the inherent flexibility of fuzzy makes it possible that you introduce a fuzzy concept not necessarily in functional analysis, in any area of mathematics, in quite a number of inequivalent ways. And so, if you want to say, or if you want to have a discussion on fuzzy mathematics, which fuzzy metric space, which we are doing this afternoon, you can see that what is a metric space? A metric space X, D is a metric space essentially where D is a function from x cross x to 0 infinity. Sure. So you can introduce fuzziness in very different ways into it. What is very different way? You can make this function into a fuzzy function. You can treat this set into make this set into a fuzzy set, and also you can make this function a fuzzy valued function even. That means if here is xy, then dxy is a fuzzy number. In this way, you can also introduce fuzziness in metric space. So quite a good number of ways are there. So what I am trying to tell is that Professor Biromani did a good job and a great job. Why? Because okay. এটা বড় হচ্ছে না, এটা লার্জ হবে কি করে? Down, 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 further down, further. You had been introduced to, I mean this one. This is an example. This is the definition of fuzzy metric space, which was given by Professor Biromani along with his student George. This is George Biromani fuzzy metric space, we call it. What is the essential thing in it? The essential thing in it is that its topology is a Hausdorff topology. And if you want to have a successful development of metric fixed point theory anywhere in any structure, the Hausdorff, the property of topology is something which you require often. If it is not there, then it is not that the fixed point theory will not be possible on that space, because we have very developed versions of topological fixed point theory, but in many cases you will have to take great pains for that. But once you have a Hausdorff topological space, which it is that the metric given by GV fuzzy metric space naturally induces, then you have the privilege of developing such theories in that space. And this is one of the reasons why very successfully and in a very large way the literature on fixed point theory and related theories like coincidence point theory, now proximity point theory, etc., these have come up in a very large way in these structures. So what the structure is like, I will come a little later. Before that, I will go back to the consideration of Banach contraction mapping principle. I think in your postgraduate courses even Banach contraction mapping principle is included, so I need not repeat that. But essentially it is that it should be a complete metric space. Without completeness it is not possible, and this is the great genius of S. Banach, the idea of completeness which is used in it. The Banach contraction mapping principle, it's a Banach contraction if T is a mapping, self-mapping from x to x is less than equal to k dxy. This is a Banach contraction. If the space is complete, then what you have is that you take any point x0, then point tx0, then t square x0, it will finally go to a point where you will find x bar is equal to tx bar, and it's unique. This is a fundamental result, and surprisingly enough, this result has played a very great role in shaping many parts of mathematics and its application areas. For example, the famous mathematical physicist Frankel, he remarks that the existence of flow theorem is the most important theorem in applied mathematics, which connects mathematics with physics. And if you go into the proof of that particular result, then you will see that at a fundamental level, it is using Banach's contraction mapping theorem. This is one of the examples. Examples abound in literature. So one question is that whether we can make this contraction weak. I will come to the consideration of metric space a little later. Whether we can make this contraction weak. How to do that? So we can definitely make it weak, and this was suggested by Albert in 1989 in Hilbert spaces, and later in 2001 it was Rhodes in a paper published in Nonlinear Analysis. What it is that he introduced the idea of weak contraction less than equal to dxy minus then phi of gxy. Phi is a function which need not be which has to be upper semi-continuous. So this was the idea of the Rhodes. This is called the weak contraction. And one observation over that, this is not a new result. This is actually contained in a result which was previously published. Then why it is important? It is important because simply for one reason, that it is a source point of a thought which makes possible and gives new results, or rather initiates new results in different directions, which is not confined by the result which covers this one, and gives a new chapter in mathematics. So there are several results on weak contractions dealing not only with dxy and minus phi dxy. There are different types of this type of inequality which have this one, something minus of this thing. This is a form which has been recognized in fixed point theory as a class of inequalities which are called weak inequalities. And this type of function has been referred to as control functions. Several types of control functions have come up. I will give you one or two examples of that. Just minimize that. Minimize it. Minimize. Oh, there. Suppose we can have possibly this one. No. No, anyway, going back.
Just come to the next. Just come to the next.
Oh, come to the next.
No need to. Just click on the next.
Where is the next?
Which one?
Oh, I cannot see it from this angle. Where is the next?
Which one you want?
Next one.
1 or 2?
1. 1.
1.
No. You come to FTPM here. That's that one. Just second last. Just you click on it. It will be better. Just go. This was also one of our results. As I told you, that I will basically dwell upon on our research experiences that we are having with this particular field. You will see that finally we could generalize the whole thing. This is for which reason that the weak inequality is like this, and you can see psi phi r limit supremum and infimum, it is greater than 0. This is the condition. So this is more involved condition, and almost all the things which are rather almost all the results which are published along these lines are covered by this result. Anyway, there are also other scopes of branching, and the branching went on. This is not the end of research. But what I am trying to convey to you is that what is its importance. Sure. Parallelly, just minimize it. Parallelly, I will tell you that if you look into the conventional proof of the Banach contraction mapping, you see that contraction is only used on this subset, or rather it will include this one also. Contraction condition is only used on this one. If you look into the proof, something outside this has not been considered, and if you ignore the contraction condition and say that I will not assume the contraction condition on areas of sets which are outside this. This is actually the orbit of the point x0. Then I will say still your result of Banach contraction principle holds. So we have this result for xy belonging to x cross x. Arbitrary choice. No, this can be restricted. What should be the restriction? This restriction is brought about by a partial ordering. You have a partial ordering, and if you declare with certain additional conditions that this will hold and that x is partially related to y, then it is sufficient. So you need not take all the ordered pairs. You can restrict it. In this way, with this philosophy in mind, came up the fixed point theory in partially ordered metric spaces. It developed, and this partial ordering also gave you one leverage. That is, you could just fit into the whole structure certain problems regarding integral differential equation, or like that. There are many others which could not be actually accommodated in an arbitrary complete metric space, but in a part of that in which the partial order is valid on chains or like that. And then you can apply your theorem now to those problems, and new applications could come up. And secondly, there is another thing. There is a blending of two methodologies. One is analytic, the other is order theoretic. You have a blending of that. So new methodologies are invited thereby. And so the whole literature then expanded in metric space. Now the question is that back to fuzzy metric space, the previous one. Okay. এটার আগে এটাকে ক্রস করে দিই। এটা যেটা খোলা ছিল এটা নিচেরটাই ছিল। Yes. So, as you learned, Professor Dorel Mihet has dwelt extensively today over these matters, and as I told you, that like probabilistic metric space, in fuzzy metric space also, because if you look into the definition, then you will see that it has a great resemblance with probabilistic metric space. Actually, this is a modification. Modification of what? It was actually given by Kremozil-Michailek, which was called fuzzy metric space, but this was a kind of probabilistic metric space. So this was modified in certain way. Modification is easy to see, but its implications are far-reaching. If you just make out with this basis a topology, then this topology is a metrizable topology and hence a Hausdorff topology. You will not have that without this condition. This is very important, and as you can see, M is a fuzzy set at which the point 0 is sacrificed. It's not a closed interval. But 0 is very important in your probabilistic metric space. Anyway, if you want to see whether the Segal's contraction that Professor Mihet had given, it is valid here, I will say it is valid. If you want to see that the Higgs result, that is the C contraction, it is valid here, I will say that this is valid. And all these are generalizations of the general Banach contraction mapping theorem, but in different directions, although these generalizations will coincide with one another when we use very specific types of T-norms like Hasek type, H-type T-norm, etc., etc. I will not go into all those things. Essentially, if you are interested in looking at the general situation where star is restricted only to continuous T-norms, these things are all different generalizations of the Banach contraction mapping principle. Now the question comes, can we incorporate the idea of partial order? That is, can we have a partially ordered fuzzy metric space? This question is not very difficult to answer. Just have that one, restrict the contraction condition in that way, and just follow the pattern of proof which was given for those theorems which are proved in that structure. In the fuzzy metric space, you will have the corresponding results. No problem. But the main problem will arise, and was difficult to solve, that whether we can make the condition weaker. Weakening may be done in different ways, but if you look at this weak contraction, you will see that it is something intermediate between this condition and the condition when k is equal to 1. It is intermediate between the two. Sure. If we put phi t is equal to 1 minus k into t, obviously k is between 0 and 1, then you just have this one. And if you just see that, omit this, but this is less than or rather less than equal to, you can put in sometimes, you do not rule out the possibility that phi is equal to 0 with some non-zero argument even. Then this is a non-expansion. And everyone working with fuzzy fixed point theory knows what is the problem of the fixed points of non-expansive mappings. Very special conditions are to be concocted, like normal structure and etc., etc. This is a great elaboration and especially this is important when you have the natural structure of the non-expansive semi-groups of operators. Actually, this is a very natural structure occurring in the operator theory of Banach spaces. So the very special conditions are to be concocted to ensure that these types of mappings, which are non-expansive mappings, are having fixed points. So this is somewhat intermediate between the two. If with k less than 1 we are having a fixed point, and then this is advancing towards this one, that is narrowing up the gap. Is it possible that if you think of something in this direction, is it possible that we have a Segal contraction or some other type of contraction and then just make the contraction constant? There must be a contraction constant to be preliminary, because contraction constants can also be waived in favor of just control functions or like that, phi, psi, etc. are in use nowadays. So let me go back to the initial or rudimentary results, which are fundamental results. So k will be there, a contraction constant, otherwise it's not a contraction. With k less than 1 and with k equal to 1, we have a condition, we want something intermediate between the two. Is it possible in the fuzzy metric space as well? So this was a great unanswered question for a long time. So I will give you some of our research experiences regarding it. You go down. So this is something, as you can see, that I think the other day Professor Mihet has dwelt upon it, so I will not go. This is the definition of weak contraction. We are using two control functions, as you can see. One control function satisfies this one, it is monotone decreasing, and the other is just lower semi-continuous with a, that is phi s is equal to 0 if and only if s is equal to 1. So I will ask you that think of the case where x is equal to y. Then what is mxyt is equal to 1 by your definition? You can go back to the definition and find that this is if and only if x is equal to 1. So if it is like that, then mxyt, this is equal to 1 by virtue of that this is 0, and there one psi is again 1, and on the left hand side you just have something less than equal to 1, which is bound to be the case. And so this is satisfied for x not equal to 0, it's not automatically satisfied, and this is actually the condition under which we will have the fixed point. Now, for that purpose, two lemmas are very important, which we have proved. This is one lemma. What is the lemma? The lemma is like this one. This is very fundamental thing. If without these two lemmas we will not be able to prove anything. If particularly alpha n tends to alpha and gamma n tends to gamma, these are sequences, and the star is a t-norm. Obviously, sequences relevant to the t-norm because they should be between 0 and 1. Otherwise, it will not have any meaning. So, if it is like that, then limit supremum of that, alpha n will go to alpha and gamma n go to gamma, then this beta n will be having a limit supremum. Mind it, I cannot write this thing without the assumption of these two conditions. If you say that I will take limit supremum of that and sacrifice these two conditions and then put some limit supremum of limit supremum here and here, then it will not in general hold. But my purpose is to make the theorem as general as possible, applicable not to any special t-norm but to every continuous t-norm, which is essentially the demand of the very definition of the fuzzy metric space given by Professor Biramani. So for the most general type of result, we have this one. This is the proof of that. Proof follows this way. And the second one is a just thing with the real analysis. If AFK is a function which is from 0 to infinity to 0 to 1, be a sequence of functions, then this is one is the left continuous and the limit infimum is right continuous. Sure, not a very difficult thing to prove. If it is given even to the graduate students as an exercise, they can also, any bright graduate student can prove it. It's not very difficult, but it have very very important consequences for us. Without it, we cannot move. Now you look into it. This is a complete fuzzy. I will see something with the proof. This is a complete fuzzy metric space with the property that xn is monotone increasing sequence and x, then xn, if it is converging to some point z, then xn and z will be related by the partial ordering. This is something, if you look into any theorem in the partially ordered metric space, you will find that this is a very common condition which is assumed anywhere and everywhere there. Otherwise, without this order theoretic condition, so we cannot really proceed. And rather in the sense that if you look into the proofs, this particular condition is used everywhere. This is why I was telling it is a blending of the methodology which is analytic and as well as order theoretic. And now you look into it, that if it is weakly contractive, if it is weakly contractive on every chain containing the orbit of x phi. Orbit means this one. This one is the orbit. Nothing x0, t, x0, t square, x0, like this one is the orbit. So it should hold on every chain containing this one, not only that with x0 as the least element. Not all chains, but with x0 as the least element. We don't require it to hold on any and every chain in the partially ordered metric space. There is one x0 like that. And you will tell me that you are supplying in the theorem with x0. Can you not find it? So if you go into the Banach's contraction mapping theorem proof, it's elementary, but you will see that it begins with any x0. But in order to have a very special choice, or rather to restrict the contraction condition, then the choice of x0 should be there ab initio. This is also something which almost every theorem regarding contraction on partially ordered metric space assumes. We have also assumed it. Then this weak contraction will have a fixed point. Proof is like that you construct from x0 this one, as because if it has a monotone increasing property, you will see that it is a monotone increasing sequence. It is nothing difficult. Now you can, as because it is going to be a chain, you can put the inequality like this one for choices of consecutive terms of xn minus 1 and xn, and then go on like this one. It is not. It is a just routine method that find this one. This is also just a routine method that you come to it. Now the question is that what is the Cauchy sequence? Xn is not a whether it is a Cauchy sequence xn. This is the principal part of the proof. How do I prove that? So let me go back to the. Let me do some board work. Then it will be more clear. What is the Cauchy sequence in this space? A Cauchy sequence is like this one, xn, which is a Cauchy sequence in the topology. That means if you are wanting to translate it or see it in terms of the metric which you are using, this is given epsilon greater than 0, there lambda greater than 0, there exists n, that is a natural number depending on n lambda, such that m xn epsilon is greater than 1 minus lambda for all mn greater than n. So looking technically into it, you can see, if you go back, that the topology is actually generated by a basis which has two parameters, t and r. Sure. So in the Cauchy sequence also naturally two parameters are just arriving. Sure. And so if it is not a Cauchy sequence, let us arrive at a contradiction by this one. This has to be violated. What is the point of how it can be violated? So we can just follow this point. If it is to be violated, then we should have some epsilon and some lambda for which no n exists, in which case for all mn this is going to hold. That means for all k and choice of Mn you can, without loss of generality, assume by virtue of the symmetry of the definition, n is greater than m, such that this inequality is not holding, violated. Sure. Then there is another story added to it. So n is greater than m. Sure. So make n lesser and lesser. At one stage you will make m is equal to n. Sure. At that stage what you have? It is equal to 1. When m is equal to n, it becomes 1. So at one stage you will be just violating this 1 minus lambda going into it. That is greater than will be violated to make you less than equal to in the whole process of reducing n to m. Am I correct? Am I clear to all of you? So in that case, you make a choice of n which is minimal. That means if you make nk minus 1, then you are again satisfying this inequality. This is actually the case like this one, that with mk you have, this means that this is epsilon lambda neighborhood and this is nk. Sure, this is mk, this is nk, m xmk xnk. This will be outside the neighborhood, means that this one is something which the neighborhood will satisfy. Outside the neighborhood will be less than equal to will be satisfied. If you want to enter to go there, and you will definitely reach this place by making nk less by 1 consecutively, and you reach here, that means at one stage you entered the neighborhood. So you just mark that stage, just before you have entered the neighborhood and just you entered the neighborhood, there is a change of the inequality. So this is essentially the whole thing. And so with that thing, we have this choice. Then, we come down. We have, as you can see, we can write this one. This is the triangular inequality allowed, and we take this one. Already these are consecutive terms. When you make k tending to infinity, these will go to just 1. This one will also go to 1. Then you take this one, h1 is equal to this one, the limits suprema. Apply that lemma. You have that result. Again, from the very definition, from one result which was proved by Lopez and Romaguera, the m is continuous in all variables. That we have given in a lemma beforehand. So it's sufficient that I tell it, not just show the lemma. It is a continuous in all variables. And that will finally lead to the fact that the second inequality, the second lemma we had proved with the real numbers. Let me show you. This one, the first one, and this one is the second one. mknk is given by the parameter k. So in that way, you just apply this lemma down to here, where it is. I think a little bit earlier we are leaving it. Yes, h1. So h1 is left continuous. So take s tending to 0. There is no difficulty in taking s tending to 0 because you required s to be positive only. You can take s tending to 0. So less than equal to 1, you can see. In this way, you also have with the same thing you have with h2 a function from greater than equal to 1, and finally combining you have this result. Twice S, etc. Again an application of the lemma, successive application of the same concept. Then you reach, after this you reach a contradiction. 1 minus lambda is not equal to 0. So these are routine steps actually, which argument I have given. This is 3 or 4 times repeating the same argument and just amalgamating, just fixing the nuts and bolts of the whole thing, you obtain the whole thing. So we have a contradiction and this is a Cauchy sequence. So it has now it is a fixed point. Proving the fixed point is also quite, Hausdorff topology is a must for that. Proving the fixed point is also a very routine matter, it does not matter. Now the fixed point is unique. It is also a routine matter if you have followed the ideas involved in any fixed point theorem which has uniqueness. It is like that actually, with obvious adaptation to the new inequality they are out there. Now how it is then, how it is that some fuzzy-Banach contraction mapping theorem is extended? You look at it. I will give 2 examples of this function. If I fail to give some example, that I give some conditions and etc. for certain functions, and I fail to give examples. This is quite not very meaningful from the point of view of mathematics, because you will have to sustain the whole thing with examples. That there are actually such things. We are not speaking quite in abstraction. This is very real. So this is psi is an example, and phi then make it dependent on psi in some way. This is the way. And then you will see that this one is satisfied. What is this one? This one is fuzzy Banach contraction mapping principle. How do you come to that? Just you see that this fuzzy Banach contraction mapping principle is very different from the Higgs contraction, is very different from the Segal's contraction. This is actually given by Gregory and Sapena in their celebrated paper. Now, how it is fuzzy Banach contraction principle? It is very easy to see. Suppose XD is a metric space. No problem. Then I can make X into a fuzzy metric space. Just write M XYT is equal to T by T plus dxy. Just you see. All the conditions are satisfied. You will see for all t greater than 0, this is going to be greater than 0. Sure, mxy is equal to myx. Then the other conditions, a little bit of 3 or 4 lines of calculations will establish that all the other conditions are satisfied. And in this case, what you have is that just put it back here, you will get the Banach contraction mapping theorem. So what actually is there? This is the connection between metric and fuzzy metric space. That means given one metric space, you can create a fuzzy metric space. Right? So put it there, you get the Banach contraction mapping principle. So it's another fuzzy metric generalization of Banach's theorem. In the sense that if we have the Banach's theorem, then we can create a fuzzy metric space in which that Banach's theorem goes to, fuzzy Banach's theorem. This does not mean that all the fuzzy metric spaces should have this form. But this is one example of that one. And so this is in that sense a generalization. It is proved in literature that this Banach contraction mapping principle, its fuzzy version is different from Segal's contraction and is also different from the C contraction of Higgs. This is another generalization. As I told you, that there is an inherent flexibility in the fuzzy. And this inherent flexibility gives you the opportunity that carry into the fuzzy domain the concepts you have in a metric space in several inequivalent manners. It's a privilege for you, it's a flexibility for you, and it's a freedom for you. So this is a generalization of that. And particularly, it's weaker than that. How do you know this is weaker? Yes, I will give you an example, then you will understand that this is actually weaker. So what is the example? Example is like this one. A very simple example, x is equal to 0 to infinity. X is related to y when x is greater than equal to y. The reverse way of going. Sure, the reverse way of going. It is not less than equal to this is. This is the reverse way. This is the classical definition, one classic definition of fuzzy metric space, often used. We have also used that, and any continuous genome. Sure. If x is equal to x square, then it is a monotone function. Consider the element x0 is equal to c, where we had to be given with some x0. Yes. Then it is the least element, c square, c to the power 4, etc., etc. For your reverse ordering, this is the least element. And you will see that contraction mapping really holds with this phi s is equal to where it is again with the choice of phi s is equal to this one, psi s is equal to this one. These two are choices. So you can see the contraction inequality is satisfied over that. So everything is satisfied, and you will see that yes, it satisfies the theorem. It's a weak contraction. And if you make a choice, it is not, the fixed point is not unique. And further, this is a discussion. This discussion shows with certain remarks that if you, particularly with Hasik type and etc. genomes, you can see that the Gregory and Sapena, the contraction mapping I have shown, that does not apply particularly to this theorem. If Tk is taken equal to 1, that means the non-expansive mapping corresponding to that contraction by putting k, obtained by k is equal to 1, will not be applicable here. So that we have something in between the Gregory-Sapena fuzzy contraction and the corresponding non-expansion, which is given by this one. This is the weakening of the old situation. So this is one way of doing. Now, the question remains, so people in metric space was not satisfied only with the study of just the weakening of contraction for the case of Banach contraction. There were several other contractions in different aspects. These had to be addressed and were actually addressed. So can we do something here in the fuzzy metric space? So for that purpose, we were considering some new situations. One situation is like that. And before going to that, I must make one remark. That fuzzy, there is one criticism. Fuzzy metric space is a metrizable, gives a metrizable topology. So when it is a metrizable topology, so treat it as a metric space and do anything and everything what is new in fuzzy metric space. Essentially it is a fuzzy metric space. It is a metric space with a metrizable topology and do anything and everything with that one. The answer to this one is that metric may not be known. And from the topologist's point of view, dealing with metric space and dealing with metrizable space is not one and the same thing. Dealing with metric space and dealing with metrizable space are not one and the same thing. So there are lots of theorems regarding metrizable spaces. Once you discover the particular way by which you can know the metric, then the studies will coincide. But in lots of topological situations which prevail, the metric is not necessarily known, and then the techniques of topology that largely develop for metrizable spaces is quite different from those which are available with metric spaces. And this is the basic reason that we should take up the study of fuzzy metric space as a study which is very different. It should be very different from the metrizable space. This is one thing. So there can be the other side of the criticism as well. So fine, let us see that it is not possible that to find the metric, etc. So let us wait for the time in history when we will be able to know what is actually the fuzzy metric, which is actually the metric which can give the actual metrizing metric of a given fuzzy topological space or fuzzy metric space. Let us wait for that time. But the reverse way we can see, there is a metric, and this is the very particular way that you can generate the fuzzy metric. It is, I should say, the fuzzy metric is more brilliant and more versatile. In what sense? That you can see, just look at the Banach contraction mapping principle that we are discussing today in the previous lecture also here, that you will see that it has many versions, many generalizations in the domain of fuzzy metric. Then why don't you just absorb the study of metric into the domain of fuzzy metric? You can do that by bit of the same logic. That just you have a metric, you can generate the fuzzy metric, and you can absorb any and everything in the domain of fuzzy metric. So abandon the study of metrics, go on with the study of the fuzzy metric. It can be claimed. But yes, given the situation, there is no in principle, there is no to it, really so. But the point is that the metric space study is a vast one, and we do not know how to translate with this particular translating code of transforming metric to fuzzy metric, how to translate any and every aspect of metric to fuzzy metric. Sometimes the translation is bizarre. Suppose one thing is that in optimization, there is a large scope of vector optimization just understood in metric space, because it is a very general structure. When you go to the vector optimization, it is with the Banach space structure or like that. If you want to get rid of the geometry of the Banach space, just make a filtering out of the geometry, see into the basic elements which can be treated metrically, put it in the metric space and make this study. It's a very successful study. If you want to put it back into the fuzzy metric space, then a researcher will know that what is actually the difficulty in doing that. An unmanageable thing in fuzzy metric space will be coming up, and there is no point of dealing it in that way, and rather we do not know how to deal with it. It's a very technical point. I don't think I have been very convincing to you, but to be very convincing to you requires that type of technicality with which I cannot deal just in a short span of time. Clearly. So that thing, that is the two-way traffic, that thing warrants that the study of fuzzy metric space should be a very different one from the study of metric space. It's relevant what I am trying to tell. Just put it off. Just close it. No, just. Oh, from the mouse. This one. Then I will come, I think, to this one. No, this one, not one. Just next is one. This is from one of our papers. That just go down. It was possibly in 2013 in fuzzy sets and systems. Go down. This is a coupled metric, a coupled fixed point. What is the coupled fixed point? I will just take the substance from it. Just go down. Down again. Further down. Further down. further, just that is, I think a little bit up, a little bit down. I mean, a little bit down. Yes, this one. As you can see, that this is a coupled fixed point. What do you mean by a coupled fixed point? Coupled fixed point is essentially a fixed point on the product, when relating to the product space. That is, f from x to x, you have fxy is equal to x and fyx is equal to y. As you can see, the concept was floated quite a long time back in 1987, but this was the concept gained attention from the researchers only after 2006, when Lakshmikanthan and Bhaskar was presenting their coupled contraction mapping theorem. So there are also certain criticisms with this one, because actually this can be also be obtained from just contraction mapping defined on product spaces. This can be done actually. So there is no denying of the fact, but the point is that it is another view of the whole thing. Why should we revert the two views? There are also technical reasons for that. I am not going into the whole thing, but the elaborate arguments can establish that just pointing out this point will not make the study, a separate study of coupled fixed point and coincidence point, redundant. It will not make that. So go down. So this one is something like this one. This is the commuting one, and this is the definition of compatible. You know what is the compatible mapping? This is actually commuting, but in the limit. If xn is tending to x, then if gxn and gfxn may differ. So d of fgxn and gfxn will tend to 0 as n tends to infinity. So it's when commuting in the limit, this is called the compatibility, and this is the compatibility definition with one coupled function with a single function. Actually this stemmed from Lakshmikantham and Sirik, this paper, and then we extended the idea to compatibility. Sirik, I should remember Professor Chirich. I often wrongly tell it as Sirik. It is actually, the name is Chirich. So he passed away sometime. He was a very good friend to our group actually. So we really lost one friend in him. So anyway, this was something like, the main theorem was like this one. This was Hazik-Tati norm was used, and with the help of this lemma, the main theorem obtained was this one. As you can see that the idempotent elements of the Hazik-Tati norms have been used, and this one is this, and this is a coupled contraction mapping where gamma is a control function, and the existence of gamma is proved by the limit of the idempotent theorems elements which is involved in the construction of the Hazik-Tati norm. So essentially this result is not valid without Hazik-Tati norm. Anyway, it's not my point. I will go to just close it. Anyway, for that concept I required that this one. Then I will go to this. Just make it. This is our result, almost recent result in 2016. Here you will find that we are using the same weakening of the condition. That condition, that theorem I showed you, and a weaker version of the theorem has been further weakened, but the weakening is now with respect to the, you can find these two lemmas have been used and the proofs have separately been given. So you can see that this is the other things are quite regular and normal conditions which are assumed, nothing very special in those, but you can see the most important part of the whole thing is that we are using a weak contraction inequality again, and these phi and psi's are now our old friends which appeared in our previous paper. With this it is possible, and it has been possible to show that coupled fixed point theorems, established coupled fixed point theorems, if we make a special choices of these one, and then we will find that this is the result of Lakshmikantam and G. Rich, which was in nonlinear analysis, I think in 2010 it appeared like that, if I am not mistaken that much. 9 or 10, 2009 or 2009 might be. So it was possible to make a weakening of that. And what is the weakening? And then further, if you look into the example, you will see that the example is like this one. As we quickly pass, you can see that this is the way that we use the lemmas, the two lemmas particularly, and down to here we will encounter an example. This, not much time left, but something more to say. Anyway, this is the example. You will have another two choices of phi and psi here. And this example finally will give you, we have elaborated this example quite, and it's quite a large elaboration in this paper. I did not give this elaboration initially, but the referee asked for that elaboration, that they give it elaborated in the paper. So it was not under my initial will that I have given it. It's the will of the learned referee that we did it. Anyway, so this one is that. Here you will also see that we have combined the partial ordering in this also. And the example is like that. My original theorem contains properly its corollary, because corollary is not applicable to this particular example. So it is properly contained and etc. This one, there is something conclusional like that. The basic thing is that we could also apply the same technique of weakening the contraction also in the case of coupled fuzzy fixed point theory. Now I will pass on very quickly, because I have not much time left out. Pass on very quickly. The point is that we initially began with a goal. What is that? From the point of view of, not from the point of view of weakening the contraction, but the point of view of restricting the contractive condition to suitable subsection of ordered pairs collected from the mother side. So he used partial ordering. So another method came, which are called the admissibility conditions. They were given in recent literatures. What is an admissibility condition? You do not assume anything on this space. There is no partial ordering, but you assume something more on the functional behavior. I will not be. It would have been better if I had dwelt on something on the metric space separately, but I think I have not that much of time. Just go to the next paper. Just close it. So one thing, it should be very clear that what I am, just elaborate it up. It's going down. Just make it. I live. No, it's down. Further down. Further down. Further. It's with the general matrix. Yes, here. A little bit more. So one thing must be clear, that what I am talking and basing is just our research experiences. There should not be any impression that the line is being explored only by our efforts, because there are also parallel developments, and because time is very short, I am not going into the vast literature of that. But after we had published these papers, then many other papers are coming up citing these techniques, and these techniques are being successfully applied. I have seen at least 4 or 5 papers coming up with this one. Anyway, so this is another direction. He will also see that that particular 2 lemmas are very useful. This is that we are going to, in literature we have alpha psi contraction. A type of contraction was given by Samet, I think not earlier than 2014 or 2012, I don't remember actually. If I go into the, go down into the references, then I think we can recollect, just down to references. Samet, go down a little bit. Samet and vitro. This was in 2012, I think. 2012, but then go up to that position. This was an alpha psi contraction. Nothing was assumed on the metric space on which we will act. Nothing was assumed. But some additional conditions were assumed on the functional behavior itself. What is that? That is the admissibility condition. Yes, that one is the admissibility condition. That is one size there. It will be, I think, just go up. Admissibility condition. What is an admissibility condition? F is a mapping from X to X, you can find. And there is alpha, it is with respect to alpha, and alpha has no restriction. There can be admissibility condition with any function. So alpha has no restriction, it is x cross 0 infinity to 0 to infinity. Positive real value. And if it so happens that if it is greater than equal to 1, then alpha of fx fyt is also greater than equal to 1. Then we will say that it is alpha admissible. Fine. So with this alpha admissibility at hand, we want, again you can look into this one. This is again particular for particular choice of psi, and for particular choice of alpha is equal to 1 always, because there is no restriction on alpha, it can be equal to 1 always. You can make a choice. So it again drops down to the contractive condition of Gregorian Sapena. So this generalizes this one. It's not maybe categorical that we have shifted our attention now from weakening the condition to generalizing the. This is a very separate type of problem that which we are going to deal now. To deal with this problem, my point is that these 2 lemmas again will be useful. So let me go down. These are the 2 lemmas. Just go down. Because all the papers, because you will be asking me that why don't you refer these lemmas to one paper, why are you publishing it in 2 different papers? This is a point, and I will give you the proper explanation for that. Is that these papers were almost simultaneously communicated, and I had to put the lemmas in both 2 or 3 of these papers. And so I had no other option to refer to any one of them and just cite some others. So just go down. And this is one. If alpha, it is alpha admissible, and there exists something x0 that you can also see that in the case of partially ordered metric spaces or fuzzy metric spaces, we have also the choice of an initial choice of x0. This is important. And here also we have an initial choice of x0. You can see for which this condition will hold. There is another condition xn, which is this one, that alpha xn plus 1 is greater than equal to 1 for all n, and if xn tends to x, as n tends to infinity, then alpha xns is greater than equal to 1. This is another condition. I will remind you of the condition that is often assumed that in partially ordered fuzzy metric spaces or partially ordered metric spaces, this is the ordered condition, xn is monotone increasing and that xn is tending to z, then xn is less than equal to z. This is assumed, often assumed. You look into the papers, you will see that almost all the papers are assuming this condition, without which the proof is, rather it is very strongly used in the proof. It's a regularity condition. This one, and you take at it, and there is a point x0, then less than equal to tx fx. These are the two conditions which are very much prevailing there. Now look into it. Is there any relation between the two? So this is the point that though if you look into the proofs, then what is the role of this set of conditions of orders which you assume on this space will be just played by the conditions which are assumed on the function, not on this space. So will the assumed functions generate in a very natural way a partial order to give these conditions, or a partial order is sufficient to restrict or to generate some alphas which will be obeyed by this one? This was a question. Similarities of the proofs will suggest that this question should be investigated. We also tried to look into the matter, but to no avail. Still to no avail. We could not in any way, we tried, but could not in any way still now generate any connection between any relation or connection between the admissibility conditions and the conditions of partial order. It is not yet intelligible, and I have not ever seen in recent literature such things appearing. So, just a little down. So you can see that there is the construction like this one. Then please go down. There is the inequality is being applied. Then further down, the psi n with the size property, it's just up, with the size property just down. It's quite a routine matter that we prove this one. Again, with the Cauchy sequence, same technique. Go down. But now, within the technique, there are variations. Go down. It's not possible to just give the explanation of this proof that we gave in the first result, but there are certain variations. So just go down, just not a mimic of the previous one. Down. Again, there is a contradiction finally. With this contradiction, we have, yes, there is a contradiction finally. The contradiction is like this one, less than this one. And again, with that contradiction, we finally end up with the properties of that. It has a fixed point next. The example will be there. Go down. The example will be there. This one is the example, not a very illuminating example. We could not find a better example here. But this example amply gives you that this particular mapping is not going to be a contraction mapping. Although example looks simple and not very illuminating, but you see the existence of 4 or like that, which when calculated will definitely give you that this is not a contraction. It's something alpha psi contraction which is other than contraction. So go down. So this is actually proved that, thus this shows contraction is more generalized contraction than Gregory's happen. It does not apply to this one. So down. I think this is the end of the result. So just close it. Now the point is that these were our experiences of generalizing and weakening the contraction mapping. Now you think that by contraction mapping we do not necessarily always mean that it is a Banach contraction. There are several other types of contractions. And if you look into the history of the contraction, then you will see that for quite a long time, until the end of the 6th decade of the 20th century, that is about 40 to 45 years, Banach contraction mapping theorem stood in isolation and solved mathematics by providing different methods, the fixed point methods for applied mathematics, or rather application areas of mathematics, if applied mathematics a little bit misnomer. But after that, new contractions were just on this way. The first of its kind came from the work of Kannan. Kannan gave, and why it is remarkable? It is remarkable for many reasons. Suppose this is the Kannan type contraction. D tx ty less than equal to k by 2 d xtx plus d yty. And this is Kannan. And there is Chatterjee type of contraction. It's somewhat dual. You will see that it looks like a dual of that. Somewhat dual xty plus y dtx. So if in a complete metric space these two inequalities are separately satisfied, they will also give you not only a fixed point but unit fixed points. What are the specialities in it? The great speciality is that Banach contraction mapping is a continuous mapping, but these are not continuous necessarily. And there is another speciality. Both are from India. That is Chatterjee, but I met the daughter of Chatterjee's and I asked him how it is that it is he. So he gave me a rebuff. What is the spelling of T? What do you write, T-E-E or T-E-A? So I told T-E-A. So why it is not Chatterjee? So she told me like this. So anyway, so this is more remarkable that both are from India, and for me there is additional thing to be remarkable that both, when they were creating the conditions, they were both from my city, Kolkata. This is also remarkable from my end. So anyway, after this was Chatterjee did not obtain proper recognition during his lifetime, but Kannan did only one work, rather two works, one published in Calcutta Mathematical Society Bulletin and another in American Mathematical Society Proceedings. These two introduced discontinuity in fixed point theory. So the chapter of discontinuous fixed point theory is actually followed. This is a great thing. Now question is that, are there fuzzy counterparts? Yes, there are fuzzy counterparts. Can they be weakened? Question is yes, they can be weakened, but it remains to be weakened in the fuzzy domain. This is an open problem in fuzzy domain. And another thing is that, have they been weakened in the metric space? Answer is yes. There are quite a good number of papers in weakening the Kannan type and Chatterjee type resistors. So this is an open question, open problem, not really that much of question. I don't think it will be very difficult to weaken all these conditions by these types of techniques which we have discussed. So the problem remains to be just solved and done actually. And the second thing is that there is another domain in fuzzy which is quite not touched yet. A vast unexplored domain remains, that is multivalent. the first multi-valued fixed point theorem, I think I am finishing, but I will take another 5 minutes, I think. Just. This was given by Nadler in 1969. They used a particular concept of Hausdorff metric. What is the Hausdorff metric? Hausdorff metric, if we don't write out the whole thing, if it is a set A, if it is a set B, then you take this distance, the maximum of the minimum, and then you take here the minimum distances and then maximum of the minimum, and then take the maximum of the two. So this is going to be the maximum of this one to pictorially understand the whole thing. So if A is equal to B, you see that the things are juxtaposed and the distance vanishes. Other things are there, but one thing is important, that they should be closed sets, and not only that, closed and bounded sets. Even boundedness can be excused by some bit of argument there, and this particular work of Nadler has not yet been carried into the domain of fuzzy mathematics. But fortunately, in 2004, this was Lopez, along with another, who introduced fuzzy Hausdorff. Sure. So we were just I will show and then I will leave. Just cross it out.
This one?
No, not this one. I think this one might be. No, not this one. This one. Yes. Just make it. Yes. This one we were trying with. This paper is actually not yet published. Just just a communicated paper where you can see that this is the fuzzy concept of fuzzy Hausdorff metric, which was given by, that I told you, 2004, it was Lopez. This was the definition of Lopez. And by exploiting the definition of Lopez, we could really see that we have another fuzzy metric space with the fuzzy Hausdorff metric, and then this is fuzzy multi-valued Carnot contraction, and what we could prove is that fuzzy Carnot contraction will have a fixed point for that. Not only that, there is another thing which is more relevant for multi-valued mapping. So what is that? If you have, this is the type of thing which is normally very important in dynamical systems. The thing is like this one, that if you have, generally you know that the functions of operators do not have fixed points. But if the thing is like this, Tn is a functions, and every Tn has a fixed point xn, not a unique necessarily a fixed point, set of fixed points xn is equal to txn, these types of things, so call it fxn. Sure. And if Tn in some sense may be uniform convergence, or there are other types of convergence of the functions, it goes, then whether fxn will go to ft. This is the question of stability of the fixed point. That is, the fixed point of the sequence will go to the limit of the fixed point of the limit. To be heuristic and loose, to speak it in a loose sense. So, what should be, and what is this one? If these are sets, then you should use the fuzzy Hausdorff metric to make sense out of it. Actually, in your metric space study, this is there with the help of the Hausdorff metric, and so for that purpose, we could define this stability, the concept of stability, and we could show that if we consider the multi-valued fuzzy Carnot type mappings, which are necessarily discontinuous, we have given also discontinuous examples, they will have the fixed point stability as well. So what I am trying to tell, that there are, starting from this position, you can see that weakening of the contraction is the great task which remains in the fuzzy domain. Now this, insofar as our knowledge and our search for literature goes, it is extensive with Elsevier, Taylor and Francis, and Springer type journals, and some other journals as well. So the multi-valued fuzzy fixed point theory has not yet developed. So at this entry point there is a vast field which can be approached. So I think that I have taken a little 3 or 4 minutes more time, and I should stop now actually. So I had in mind to give you some other ideas of how the theory can expand in some other directions. Anyway, I should restrict myself and stop here. Okay, and I will invite questions if there are any. So you can close.
So where we use the property of lower semi-contained?
If you go into the proof, then you will see that this is minus of something, and so it will automatically be like that. You need not require the strong property of continuity. It's sufficient.
After lunch we have the discussion.
We have the discussion session.
Every research work established in metric space can be converted to fuzzy metric space?
No, but I think what I told you, as because every metric has a corresponding fuzzy metric. Every metric has a corresponding fuzzy metric. So in principle you cannot deny that the function or the concepts which rest essentially on the metric and not on anything other should be convertible. But what type of daemon is created by that conversion, we do not know. Whether we can manage with that daemon or not. And daemons are really created for that, because some certain conditions which are very elegant, and if you just look into it and you will have a tendency to work with it, something becomes very bizarre or something like that if that transformation is carried out in that way. So in principle you cannot deny, provided those considerations are only dependent on the metric D. But there are large parts of metric studies where there are concepts which are not sole functions of D. There are also other structures defined, external structures defined, etc., which will require extra efforts or extra considerations for such transformations, which will depend on the particular case whether it could be done or not. That's that. But insofar as our contractive fixed point theory goes, yes, a contraction is definitely just a metric dependent thing, and it can be converted in some way, whatever be its form.
Okay, thank you very much.
Okay, welcome.
For the lunch purpose? Yes, sir. আপনি পুরো 7 অবধি আছেন?
7 সকালে যাব।